Good afternoon and welcome to this week's episode of the CERIAS Security Seminar. So bear with me for a second. In 1992, Purdue's COAST laboratory was established in the computer science department here, which was one of the very first computer security labs that was established in the world. In 1998, COAST transitioned into CERIAS with a grant from the Lilly Foundation. And with the primary difference between COAST and CERIAS was the opportunity to be able to take a look at cyber and cyber physical security from an interdisciplinary perspective. We've grown over the last 22 years now, including more than 135 faculty from 18 different academic departments across 8 different colleges. So I think we are absolutely, truly living that interdisciplinary mission very well. But if you take a look at our speakers over the last 20 plus years, no surprise, many of them come from computer science departments or electrical engineering departments or applied computing departments when they come from academia, or they work within typical IT organizations or within cybersecurity organizations within corporations. So it's always rewarding for us to be able to invite a speaker who comes with a unique perspective to that, and that is certainly the case today. So it's my great pleasure today to introduce Professor David Henthorn. David is from Rose-Hulman's Chemical Engineering Department. Dr. Henthorn is an expert in biomaterials, biosensors, and polymers in medical application, but his research includes the modernization of industrial control systems, including the major push to enhance the cybersecurity of all critical infrastructure. David, welcome to Purdue.
Thanks. Yeah, I wanted to talk today about educating the next generation on the challenges of securing critical infrastructure. Like the introduction said, I'm a chemical engineering professor at Rose-Hulman Institute of Technology, which is in Terre Haute, Indiana, which is actually just downriver from Purdue on the Wabash River. So you can throw something in the river and then eventually I'll get it down here. So real quick about me, my chemical engineering degrees are actually from Purdue. My bachelor's and PhD degrees are from Purdue University. And I've been teaching chemical engineering at Rose-Hulman since around 2012. My main areas that we teach and do research in are industrial control systems, chemical plant design, and applications of data science, then especially in process technology and process automation. But my interest was always in combining computers and chemical engineering or chemistry. And so I'll give you a picture of a place kind of like my first job, my first internship as I was a chemical engineering student at Purdue. My chemical plant didn't look this nice. I kind of fancifully wish I had been at something this nice looking, but it was a combined chemical and pharmaceutical facility with adjacent research facilities. And I was hired there, even though I was a chemical engineering student, I wasn't actually hired as a chemical engineer. I was hired in the IT department. This is in the mid to late 1990s. And they're starting to see this big expansion of all these devices that are getting hooked onto the network. And so they're hoping that at a chemical plant, maybe they could have a chemical engineer being able to run in back and forth between the IT department and oftentimes what we call the OT, the operations technology department. And we'd be able to run back and forth. And so in addition to my sort of normal network admin sort of duties that I was doing there, also just digging around everywhere, trying to figure out all the different assets that were being plugged into the network, whether they were expected to be there or not. So I spent most of the summer running around, just tracing cables, trying to figure out who owned what and what potential threats these devices could have and all these different things. And so that was a really cool experience as a chemical engineering student, is to go in and work actually on the IT side. And so I come back to Purdue fresh off this internship, and I got very involved in high performance computing for molecular simulations. So big molecules on supercomputers. Purdue had a great supercomputer in the late 1990s, something like 70th or something like that on the top 500 list. Research wise, it was going great, but we wanted more. And so we ended up petitioning and finding some money, and then eventually my laboratory that I was doing my PhD in, we built our own Linux cluster. But while I was there were these CERIAS lectures, and even though I might have had a little bit of imposter syndrome going over to them, I went to them. And so I actually found, because all these lectures are listed online still, I found the first CERIAS lecture that I ever attended. So February 20th, 1998, lecture by Professor Spafford himself, because I wanted to hear about, well, all these things are getting networked. And what is this expert thinking about all the different privacy concerns? And I was pretty scared by the last line there. It says attendees are expected to provide comments and questions. And so the imposter syndrome was pretty real when I saw that line, but it was a great experience. But looking back through that list of CERIAS lectures, I actually stumbled upon one I didn't go to, but I really wish I had. So back in September of that year, we had William Harris from the newly formed Critical Infrastructure Assurance Office. And so a little history about that is that in 1996, there was an executive order issued by President Clinton that said, hey, all of our critical infrastructure is getting networked, it's getting we're having communications either internally or at least possibly to the external world as well. And so this has dramatic concerns from a national security point of view. And so in 1996, this executive order was issued, and I want to call attention to it that it's 25 years ago as of tomorrow. So July 15th, 1996, this executive order created the President's Commission on Critical Infrastructure Protection. And this led to various congressional hearings on critical infrastructure and how we should secure it. And importantly, it led to this commission's report, Critical Foundations Protecting America's Infrastructures, published October of 1997 or around there. Eventually, that report was put into directives. So Directive 63, Policy on Critical Infrastructure Protection, came out in 1998, leading to things like, well, the creation of that Critical Infrastructure Assurance Office, amongst other things. So back 25 years ago, people were starting to say, we need to really be thinking about how we can secure critical infrastructure, especially as more and more of it gets connected. If you don't mind me flipping back a screen here, the title of Dr. Harris's talk was Infrastructure Assurance, the Challenge of the Next Millennium. And it couldn't have been more correct about that. We are here in the next millennium, and every day we're reading about more and more critical infrastructure being attacked, ransomware, and these different things, especially in the last few months. So this commission's report lays out this 8-part strategy for securing our critical infrastructure. And central theme there, we really need to build partnerships between owner operators, so private entities, and governmental agencies. And this is actually mirrored very much in the most recent executive order that the Biden administration just put out, saying we should push our governmental agencies to really set the bar to improve and buoy the private sector up to a higher level. That whole thing about a rising tide lifts all boats. And so if we set our expectations high, that'll force vendors to meet them. And along the way, they're going to then be able to provide the private sector with much more secure products. I'm an educator though, and so if you don't mind, I'm going to jump into chapter 8 and focus on that one, the report on awareness and education. So in that report, chapter 8 about awareness and education, first of all, it starts off like saying, Smokey the Bear is this famous awareness campaign. Maybe we should have something like Smokey the Bear for securing critical infrastructure. And I've had lots of dreams of what that would look like. But on the education side, it all boils down to we must, as we plug more stuff in, as more and more stuff gets connected, we have to improve the general knowledge base throughout the entire nation on cybersecurity skills, basically. And so they split that into two separate things, professional and general education recommendations. So on the professional side, we wanted to recommended to expand capabilities of higher educational institutions to teach information security. And at the time, after some congressional hearings, in which case actually Professor Spafford was mentioned and then cited in this report, his fact comes out that only 4 institutions at that time were teaching information security at the PhD level. And so that dramatically needed to improve if we want to improve and secure our critical infrastructure. So their recommendations on that front: support professional conferences, additional research grants, and these different things in this area to build up professional capabilities in information security, with the idea that at the PhD level, those people will turn into the next educators at the college level, who will then turn into training the next people that are training at vocational schools or high schools or whatever, and then trickle it down that way, but build at the high level, the PhD level information security. On the general education side, They came through and said, well, it's deficiencies in the training of technicians. And so as a person that works with critical infrastructure, I'm a control systems person. When I hear technicians, it's the people that are there running the chemical plant day in and day out. So that's what it means to me. They're saying the deficiencies in the training of technicians are reflected in the day-to-day operations. And so we need to improve that. And I think we could have gone more in that area. So looking back now 25 years, I think we could have done a little bit more. So how did we do 25 years later? Well, in the terms of information security, huge growth, absolutely massive growth. And I think a number of people on the call would be better suited to kind of look back and say, yeah, this is how we did and everything like that. But from somebody outside looking at that saying, it's massive growth in terms of information security, how it's taught at various levels. It hasn't translated 100% though into benefits for critical infrastructure. We're seeing obviously still problems with securing critical infrastructure. And so I think it boils down to, these are extremely valuable skills that these people have if you have a high level degree or if you have great training in information security. And so market forces have split them out into various different corporations, entities, and these sorts of things. And so securing critical infrastructure competes, and I'm going to say it competes against top tier destinations. Talking to computer science or software engineering students, then they would love to go to certain companies, and less so that they want to go make sure that that a nuclear reactor doesn't blow up or something like that. On the general education side, I feel a little bit more comfortable talking about that. I'm thinking that the real world proof here kind of shows that we didn't quite hit the mark of spreading out this day-to-day operations and day-to-day training in cybersecurity to get more of the general population comfortable with cybersecurity of critical infrastructure. And so I kind of say, should this have been limited to what we would call technicians? I think it could have been more of the general population, and especially people that design critical infrastructure. We missed the boat, clearly. So what else happened in 25 years? Well, I mean, the big caveat here is September 11th, 2001 happens. New executive orders come out from the Bush administration, and that led to a large reorganization of how we, at the governmental level, how we handle critical infrastructure and who guides people in those regards and so forth. Department of Homeland Security, for example, was formed 2002. CIAO, which was formed under the Department of Commerce, then gets folded into Homeland Security. Homeland Security also folds in some other critical infrastructure components from the FBI and other agencies. But the big one would be in 2018, we get CISA, the Cybersecurity and Infrastructure Security Administration, and that's kind of our modern go-to administration for critical infrastructure. And so we might as well talk about what actually is critical infrastructure. So I'll use the modern definition that CISA has. CISA identifies 16 sectors, and those are sectors where their assets are so valuable or vital to the national security or the economic security of the United States that if something were to happen to them, we would have debilitating effects to our economy or national security or something like that. So 16 sectors. So in the last couple of months, we've had a number of incidents, but two of the more major ones and two of the more high profile ones, we had the Colonial Pipeline in May, which supplied about half the fuel to the eastern side of the United States. That was shut down with ransomware, and then a similar ransomware attack a few weeks later shut down meat processing plants, US, Australia, Canada. It's actually a Brazilian company. And so the first director, I should say, of CISA, Chris Krebs, was on the Today Show not too long ago, and he had this great quote that I like. They went after our gas and they went after our hot dogs. Just no one is out of bounds here about critical infrastructure. And so we've now established that critical infrastructure involves gasoline and hot dogs, but what else does it potentially involve? Well, things like dams, power plants, electrical grid, manufacturing, transportation, water facilities, food and ag, chemical plants, nuclear facilities, these kinds of things. And just remember, my bias is I'm a chemical engineer. And so if I keep running back home to control systems and chemical plants or pharmaceutical plants, sorry, those are my biases. And so you're welcome to ask questions along the way and everything like that. But if I keep running back to examples being in like the chemical field or something like that, that's just kind of who I am. So Okay, so this past year, I set out to learn more about educating students in critical infrastructure cybersecurity. And I tacked that twofold. I started contacting computer science or software engineering departments saying, hey, would you mind if I came in and like guest lectured or gave a seminar or something like that? And so I've been talking on the CS and SE side at the undergrad and grad level. What's unique about critical infrastructure? Why are we having such a hard time getting it secured? And then we typically walk through some incident reports, some famous incidents and stuff like that. And that's been really fun. I've also been working with engineering students and trying to get them to have a better base knowledge of some basic cybersecurity skills. And then thinking about how we, perhaps through our critical infrastructure design process, we actually lead to some of these deficiencies in cybersecurity. So what's worked so far? Well, just discussion questions have been pretty good. For example, here's one that popped up in May that I was asking my students. So we're talking about the Colonial Pipeline ransomware incident. And it becomes clear after a few days that their IT networks are the ones that are affected by ransomware. But the OT networks, the operations technology, basically the control systems and associated devices there, they're not affected. And so they shut the pipeline down. So they shut down all the OT networks, the control systems, everything like that. They shut those things down, but they weren't actually being affected at the time by ransomware. And so it's a great discussion question for the class. And if anybody has a chance to do this, then ask your students, if you would have been in that situation, would you have shut down the pipeline? Obviously, it led to massive disruptions in the fuel supply to the eastern side of the United States. And it was significant financial loss for that company and financial disruption for the country as a result of that. So would you have done it knowing what you did? So it's a great discussion question. And I got great questions about that. So what else worked? We hosted current events thing. So during the Colonial Pipeline ransomware attack again, we did a panel discussion. This was at night. It's virtual. Everybody's virtual these days. It's nice and easy. We invited people from computer science, software engineering. We invited an individual from our IT department at Rose-Hulman. And then we had an individual, Greg Newman, who is more on the petrochemicals, so fuels and technology, that kind of stuff side, as well as having a computer control system person, myself there. And we did a panel, and it was attended not just by students, but also by faculty members. And somehow it was also attended, like if people in the community found out. And the cool thing from an educational institution point of view, even prospective students logged on. It was really neat. It was a cool experience. But by far, one of my favorite parts has been working through case studies with students. And I've actually found a few case studies that work really, really well, both when I'm talking to people more versed in cybersecurity and people that are more versed on the engineering side or the critical infrastructure side. And so, this parallels a lot of fields that use incident reports as case studies to teach things. And so on my side, we frequently go back to the Chemical Safety Board videos, CSB. If you've not watched on YouTube Chemical Safety Board videos, I recommend you take a chance to do that. They are so informative and they're so well done. They're targeted to the general population and they're just absolutely wonderful. And it's just over and over this series of events that didn't seem probable, but yet happened, leading to this incident or that incident. And it's really, really informative. And of course, if you're doing airline stuff, NTSB and these different things like that. So walking students through here has been really great experience. And so I guess if you don't mind, let's walk through potentially one here. So first, for the computer science, software engineering students, I usually focus on what goes into designing critical infrastructure. Why do engineers, traditional engineers, those kinds of things, why did those engineers do, or why did they make the decisions that they made that led to this? What makes critical infrastructure different than the technology and the tech that you're used to working with every day? And why is it just so hard to secure? On my engineering side, on my engineering student side, I've been telling them, these are increasing in frequency. And so how do you protect your site? How do you protect yourself from these things? And then if that's not motivation enough, I basically say, here's an incident report and here's where the engineer failed to do what they needed to do and blah, blah, blah. How do you keep yourself out of the after incident reports? How do you keep yourself out of news? Out of the news, back in February, we see the SolarWinds CEO blaming an intern for a SolarWinds 123 password. I think there's a lot more to that story than that, but that person was a convenient scapegoat. So how do you keep yourself out of those after incident reports or out of the news? So one of my favorite ones to work with when I'm teaching these courses is this 2017 attack on the petrochemical refinery in Saudi Arabia. The information security InfoSec community frequently refers to it as TRISIS or Triton, but it's an attack on a petroleum refinery over in Saudi Arabia. So when I teach this, I usually provide these white papers for anyone that's interested. And here's 3 really good ones. So we have the first one from FireEye Mandiant, second one from Dragos, and then a third one's a Black Hat USA conference paper that was published from authors from the Nozomi networks. So you get these headlines: Triton is the world's most murderous malware and it's spreading, which sounds incredible, right? We walk through, we find that it's a little bit more nuanced. Well, it's a lot more nuanced than that. And it's interesting, but one of the key takeaways behind this attack, it seems that the attackers were very much interested in causing some sort of catastrophic event with the chemical plant, explosion or something like that, some major safety incident that they were interested in causing. So that seemed to be the end goal. And so we usually kick off with these things that have massive scales in terms of size. 1,000 to 8,000 acres are very typical sizes for chemical nuclear power plants, mega manufacturing, that kind of thing. And so what we frequently talk about is with students, like, what's the size of your campus? Like, just to get them a ballpark view. So this cyber attack, this petrochemical refinery attack, occurred in a place that was 4,000 acres in size. And so I looked it up. Purdue University is about 2,500 acres in size. So this chemical plant was nearly twice as large as Purdue's campus. And as a former Purdue student, Purdue's campus felt enormous, especially when you looked at that and said, I have to walk where at 7:30 in the morning? Because it seemed like all my classes were at 7:30 in the morning as an engineering student. The Colonial Pipeline itself is 5,000 plus miles long. Semiconductor fabs, we have semiconductor shortage right now, and so there's this burst of activity. Well, it's been planned for years, but the focus is very much on getting it out as soon as possible. There's this big burst of activity in semiconductor fabs, and these are 5 million to 10 million square foot buildings. And then similar with like Tesla gigafactories and these sorts of things, 2,000 to 3,000 acres are typically what Tesla looks for as a new site. And these massive systems end up costing massive amounts of money, so hundreds of millions to billions of dollars total. And we need very specialized systems then to run these things. But because they're so big and because they cost so much money, we typically design these things to have a very long lifetime. 25 plus years is easy. And so we expect these things to operate continuously and then last for decades and decades and decades. And so we haven't been budgeting enough for upgrades. We haven't been budgeting enough time, downtime to fix things and make sure things are modernized and all these different things. And so that leads to a lot of legacy hardware, protocols designed in the 1970s and 1980s. I was talking with a vendor yesterday, and we were very excited because there was a new technology based, a new physical layer for Ethernet. We're all excited about how this is going to change how we wire plants up and everything like that. It's going to be very exciting. And then we plan to just shove the normal sort of 1980s protocols down those wires and not learn from any of our mistakes in terms of like security and that kind of stuff. A lot of the controllers we deal with are so old that they lack the computational horsepower to do any sort of encryption. So authentication, all that kind of stuff is off the table. And then we're stuck with providing all sorts of backwards compatibility, and that leads to lots of cybersecurity compromises. And so once we have that equipment, because these systems are so large and complicated, we almost always have to have some vendor that supports it. On large installations, a lot of times those vendors actually embed engineers and technicians on site to help with issues, but many of the other ones are coming in through remote means. The Oldsmar water attack that happened in February of this year was through, of course, the famous TeamViewer software that gives people trouble. But maybe it's as simple as some sort of VPN into a control network somewhere. And how about patches? Well, here's a a well-known patch from this past year. So came out in August, so about a year ago. When this came out, Microsoft said, this is, it's got a CVSS score of 10.0, absolutely critical. You need to get this patch done as soon as possible. Vendors then in the control system community are saying, whoa, wait a minute. We need plenty of time to test this, because you can't just throw in a patch and then hope that it doesn't actually affect the ability for our system to make sure that your reactor doesn't blow up or something like that. And so we typically see 6 weeks, 8 weeks or something like that before the vendors give us an okay, even though it's an absolutely critical patch. And so we're typically months behind at best for patching. And even then, it's usually months behind when we get the okay for patching. And then you're trying to schedule, okay, when do we actually have downtime? When do we have downtime to go ahead and apply these patches and so forth? So critical to understanding that 2017 attack is to see that both cybersecurity and engineers use defense in depth as a defensive strategy. And the defense in depth on the engineering side looks something like this. We frequently call it layer of protection analysis. And maybe this is the first time you see it, but if you think about it, you've actually experienced this in a number of different products. Okay, so the first thing we need to do with an engineering system is, or with an engineered system, is our process design. Our design scenario here has to involve making the thing as safe and easy to operate from a first principles physics point of view as possible. So we don't want something that explodes all the time. We need to design it so it is very stable. And that's purely from thermodynamics, and that's from laws of kinematics. It's from the basic laws of physics. You want to use those to your advantage as much as possible to design a nice, stable system. But stable systems don't do enough to actually get you what you need. And so then you add a process control system or industrial control system to move them in the direction that you want. So this turns on heat somewhere, or makes something move, a motor move, or allows the turbine in a power plant to move or something like that. And so we have computational control, computer control of the process, allowing then things to be controlled but done in a very careful way to obtain our goals, but in a safe manner. If that process control fails, however, we have a third layer of defense then, and that's we start to have alarms or events happen, and that is screaming for humans to get involved. We call that operator intervention. And so this is at the classic klaxons and warning bells and everything like that, saying something's going wrong and the industrial control system isn't quite able to bring it back to a safe state. People need to get involved at this point. Over the last few decades, we've added a separate system on top of that, which is a second control system, and it needs to be disconnected. It needs to be separate from our traditional control system. This is your last line of defense before bad things happen. And the safety instrumented system, or SIS, is there to shut down things as safely as possible. And so whereas the traditional control system involves some really great and really interesting math, a lot of people use neural networks and everything like that, the safety instrumented system is very Boolean. It's, if this happens, then shut it down. If this reading looks bad, then do this. Prevent this explosion from happening by releasing pressure and these things like that. It's usually if-then kind of statements then. If your SIS system fails, then we've officially gone into a phase where we need some sort of mitigation. And then this typically is, we've designed our equipment to fail in such a way that it fails relatively safely. So we have parts of our equipment that might rupture or break in a certain way that it releases energy in a safe manner. But at that point, it's permanent damage. You'll have to shut down. So then we have this active protection that happens once we step into the incident phase. After that, you're thinking like, well, what can the building contain, or what can I do with geographical structures around me, dikes and bunds and those kinds of things. And if it gets out of hand even more, then we have the full-on emergency response. So these attackers at this petroleum refinery seem to be going all the way to this emergency response. So they're hoping to get all the way there and cause some real damage to the system. And so we can compare this to something like a self-driving car. At the base level, this process design, I want my car to be as stable as possible. I want it, as it drives down the road, to drive straight, want to go around a corner. I don't want it to flip over and all these kinds of things. That's what we're talking about. We want to try to make things from a physical point of view, from a laws of physics point of view, to be as safe as possible. And then if it's a self-driving car, the next step up would be we'd have some sort of algorithm that's going to keep it between the lanes, move it around objects, and these kinds of things. But along the way, if there's any sort of failure of that self-driving mechanism, operators are going to, so that's the human behind the wheel, it's going to beep at them and say, you need to take the wheel, you need to take over. So that's the operator intervention stage. The safety systems side would be, they're usually radar driven brakes on cars, that are braking systems that are on cars that say, I'm about to hit something, I'm just going to hit the brakes for you because it looks really bad. And so that would be akin to the SIS that we have here. After that, you start to have crumple zones in your car for the active protection, airbags, and all these different things as you build up to full-on emergency response. Okay, so this Triton incident overview, major petrochemical, 4,000 acres in size. SIS shuts down suddenly a Saturday evening in June. Vendor comes out, resets the Triconics was the brand name of the SIS. So that's where the name Trisis comes from, it's a portmanteau of Triconics and SIS. The SAS shuts down again in August, at which point then incident and response teams are called because it's clear that something else is going on here. And so since we're doing a talk at Purdue, we might as well talk about the Purdue model, which originated from Theodore Williams' his work at Purdue University in the 1990s. And his work says that control systems usually segregate or segment into these natural breaks and these natural levels of operation. So if we're going to design some sort of network architecture, then let's mimic those natural breaks that we see in control systems. So at the top, we have sort of the enterprise network. Most of these are nowadays connected to your enterprise network or your corporate network, allowing free flow of information to engineers and billing and finance and these kinds of things. At the base level, level 0 is where I have my crown jewels, robots, turbines, reactors, and all these different things that connect into the controllers that are down there at level 1. Okay, and so over here, I've now added the SIS. Notice the SIS is not connected to the network. Ideally, it's not connected to your control system network. Maybe you have some read-only controls or something like that, so you get an idea of what the SIS controller is actually doing. But for the most part, we want to have that kind of off to its side. And so we start to talk to students about this, whether they're the cybersecurity students or whether the engineering students. We built up this background and say, okay, now what's going to happen with the attack? Well, the first phase of the attack is very conventional. VPNs compromised, perhaps through leaked credentials or something like that, allows them to get into the corporate network. After a while on the corporate network, then they're able to find the right credentials that would let them into the control network. And so with the right credentials, they were able to, in this case, remote desktops, so Windows Remote Desktop Protocol, allow them to get further and deeper into the control network. And we see then compromised credentials. We see things like there were misconfigurations of the firewalls, allowing traffic to go much deeper than it should have been able to go, especially from the corporate network, and so forth. And so we see these different effects, and different groups, whether they're more cybersecurity oriented or more engineering oriented, we might emphasize different things here, but this is a very nice attack, or a very nice case study for this attack. And so one of the frequently one question that almost everybody botches, whether they're more versed in cybersecurity or more versed in engineering side of things, how long do attackers dwell in a network in days? Or sorry, in time, so minutes, hours, days, weeks, and that get a show of hands and stuff like that, and allow students to kind of banter back and forth and try to get an idea of what's going on. And almost everybody says minutes to hours. And so I show them this from FireEye Mandiant, then median dwell time in days. They've been tracking this, that as we've gotten better at detecting incidents, that this dwell time has gone down, but we're still talking weeks to months sometimes. And so that's a critical piece that a lot of our students are missing, that this gives attackers a long time to move laterally through networks, find the right credentials, and then move deeper into a process and find ways, especially when it's something as targeted as what happened here in 2017. So this is a really crucial piece that people were missing, is how long attackers will actually stay in your networks, then collecting information on everybody. And this really drives home apart. And the engineers especially are shocked by this, because there'll be a piece later on that's critical to this information. So as the attackers are moving through these networks, they get down to the low level and they basically have control of the process, which means they could, in theory, either shut the process down or they could steer it into an unsafe state. What I mean by that is that you would be able to use the control system to push things to operate unsafely if you wanted to. But of course, the safety system would say, hey, that doesn't make any sense, let's shut everything down. So the goal at this point by the attackers was to shut down the SAS. However, the SAS wasn't connected in a very straightforward way. And so they have to think of a different way to shut that piece down and remove that piece from the board. And so I asked the students, cybersecurity students and engineering students, like, what would you do at this point? And they kind of sit there and they're stumped. And then we show them the incident report and it just comes down to social engineering. Most likely, the attackers masqueraded as another person within that institution and simply emailed saying, hey, would you mind installing this piece of software on the SIS station for us, and gave it an official name, trilog.exe, and said, hey, would you mind doing that for me? And that really hits home with the engineers that people could be masquerading as someone else that would be in your own organization, sending you malicious things to install. And I look at them and say, but I don't understand. From an engineering point of view, if I asked you to go and make a change to the piping, to the electrical work, or somehow something else with the process, you'd say, well, I need to get approval for that. We need to document that and stuff like that. But installing rogue software, don't the same rules apply? Now, the cybersecurity students sit back and just kind of laugh and say, ha, like we built up this and it was almost stopped, but those pesky engineers were fooled into installing malicious software for us, and say, wait a minute. So, but don't get too cocky over there, because the next piece of the puzzle, as people were starting to look into this and reverse engineering the software used to work with that SIS controller, hard-coded credentials show up, allowing a complete, literally a backdoor. It's literally denoted as backdoor within the software. So if you get a hold of the software and you just look for a string in there, a backdoor, there it is that you can enable with hard-coded credentials, and then suddenly that very easy attack. So maybe developers need to not get so cocky at when engineers make mistakes, because these things pop up as well. So that's a really good incident we walk through, and it's informative for both cybersecurity students that aren't as well versed with critical infrastructure and with engineers who aren't as versed with cybersecurity. And of course, then these two events where the SIS shuts down, that's where the attackers then are trying to overwrite the firmware of the controllers, the SIS controllers, and ultimately it failed both times. And so that was good. And then they gave themselves away by having firmware that failed on two occasions. But you know what? The engineers have been here before. We've had massive industrial accidents for decades. And we looked at that and we did a little bit of self-reflection, said, this highlights deficiencies in the way we teach engineers. Engineering accidents like Bhopal, India, or some of the more, the oil recovery, or the oil petrochem recovery stuff, Piper Alpha, Deepwater Horizon, refinery stuff like BP Texas City, and these kinds of stuff. So we had this call to action: make drastic changes to the way we teach process safety to engineers. And so we've been working for a long time then updating the engineering curriculum. How do we add process safety throughout the curriculum? And we bolster that by incidents of industrial safety accidents and so forth. And should we be doing the same thing then to increase awareness of cybersecurity? And then obviously the thing is that I believe we should. I think we should be taking the same approach, and maybe even just taking as we build in more and more process safety into curriculums, we should build more and more cybersecurity into that as well. And so there's becomes a philosophical curriculum question. And one of the questions that we have here in the chat, finally got around to it. How do we train engineers, and how do we get this curriculum changes that we might consider? So hopefully we're here to answer your questions, James, at this point now. It took me a while to get here, but we're here. So one philosophical discussion you can have is, should we do this in terms of, should we have students take like a dedicated course in this area? Say, let's focus for one semester, one quarter, whatever it is, or multiple quarters, maybe class 1, elective 1, and elective 2, or something like that. Or Should you make it nice and modular and then spread it out into lots of different courses? So as you're working on different elements, you say, oh, by the way, here is the cybersecurity part, and then work that into your analysis, because that's the path we've chosen for process safety, and we've been very happy with it. So we call that safety across the curriculum. And so it spans all 4 years. All 4 years of engineering then now gets process safety spread out through it. Whether it's hands-on stuff or more of a traditional lecture class, there are modules that we bring in and make students work with. And so if you're designing something, maybe it's on the computer or on paper, even then you're going to have this piece where it says, well, okay, now go through and tell me, how safe is your process? Is it going to lead to any sort of incidents? And then how do we mitigate those things? And from the beginning, make sure that happens. And on the hands-on stuff, before people turn on any equipment or do any sort of laboratory, they have a number of things they need to do before they can, before they're cleared to do anything like that. So we do a hazards and risks inventory worksheet or something like that. We also do indeed offer a full course in process safety. That's typically taught to juniors and above. We were worried that that's a little bit too late. We'd like to see younger students then get exposed to those concepts beforehand. But if you want to take that elective course, because potentially that's a career choice you want to make, is you want to be a safety officer, then we have that elective course as well. So I've been proposing an idea of cybersecurity across the curriculum, especially on the engineering side. And I think that's applicable to many STEM majors. On the CS or software engineering, InfoSec curriculum, how would those change? Well, I think we'd like to make as many modules and as many experiences as possible with critical infrastructure amenable to them as well. So hands-on experience with cybersecurity best practices and labs for STEM students. Modules and learning assignments in traditional classroom courses, and then have that split where we have lots of people that are really versed in cybersecurity, being able to work with some critical infrastructure, see what's different about it basically, and get some time potentially hands-on with some of it there. And then on the other side, we have engineers that are actually designing it, saying, how do we build up our cybersecurity skills? And then what kind of design curriculum can we build in that betters cybersecurity and make sure that things move along nicely when they're doing designs. So real quick though, what about existing resources? Can we leverage them? There are a number of institutions doing fantastic cybersecurity education. And there's been a huge growth in this area over the last 20 years. And these are more independent institutions. And frankly, they're kicking the butt of a lot of higher education institutions in terms of very practical, hands-on, applied critical infrastructure, especially cybersecurity. And so I'll give a quick shout out to places like SANS Institute. In terms of like courses and certs, they have great courses for general cybersecurity, but they're absolutely one of the leading sources for cybersecurity instruction in critical infrastructure, industrial control systems. And if you're down that path, there are a number of different frameworks that you kind of have to deal with depending on your area. If you're in power, then you're looking at NERC-CIP and these kinds of things. NIST has a number of frameworks that you can look through. On the process side, we're more of the ISA, IEC 62443 kind of thing. And not only that, SANS provides tons of free content on YouTube, all sorts of stuff if you want to look at understanding how protocols, industrial protocols work, and if you wanted to like, hey, how could I pull that up and look at Modbus packets using Wireshark? It's there for you, free on YouTube. Absolutely great content. Likewise, ICS Village. This is a nonprofit dedicated to bolstering awareness of control system safety and security. And it was a physical thing you'd find at lots of major conferences, DEF CON, RSA, these kinds of things. But they've done a phenomenal job in terms of having an online presence now. A lot of educational resources are there online, but they also have these great online virtual test beds, and then they capture the flags and everything like that. You just go to icsvillage.com. So what is the role of higher education though? If we go back to that 1997 presidential report on general education, we see that these deficiencies are supposed to be addressed for computer security in day-to-day operations. So I'd say strike that part. It's just deficiencies in general education we need to address. So improve awareness with the InfoSec community to the needs of critical infrastructure by providing modules, providing different ways for them to say, what's different about critical infrastructure and how can I How can I work with what I already know and extend that knowledge into critical infrastructure? And then on the other side, the people that are more likely to design it or operate it, improve cybersecurity skills of them, and then create a pipeline. So if you want to get more specialized in these places like SANS, ICS Village, and stuff like that, these can be great destinations, but build some critical knowledge bases for more of the general population, so that they end up in these great places where they have more specialized instruction. Or maybe that's academic research. So we build up more PhD students or master's degree students or something like that. So we've been building a critical infrastructure laboratory here, where we study modernization of legacy infrastructure. We look at emerging technologies. We look at applications of data science to process automation and data. So this is typically what our chemical engineering lab looks like. Students come in and work like this. And I've been making offers to CS and software engineering students to come in and try this out. If you've ever wanted to run a distillation column, great, come in, we'll do it. And I think that's a great opportunity for people to come in and do that. We haven't had a whole lot of people in the lab, mainly because of COVID, and we've been limiting the numbers, but I hope that in this new academic year, we'll have that change. We've invited the cybersecurity club at Rose-Hulman to come in and work here. We do guest lectures and stuff like that, walkthroughs of the lab and everything like that. So the goal of this critical infrastructure laboratory is to provide hands-on experience with critical infrastructures to various disciplines, not just engineers. And then allow those engineers to get a flavor of what it's like to work with OT, IT, software engineers, and vice versa. But also provide some really interesting assessment opportunities on the cybersecurity team, vulnerabilities assessment, and these kinds of things. And ultimately lead to some sort of continuous improvement. Just keep making our facilities better and better, informed by needs on the engineering side and needs on the cybersecurity side. So interested students then can take a number of different looks at host and network intrusion detection, asset scanning, and these kinds of things. And there's all sorts of cool software dedicated on the OT side for asset scanning, because a lot of OT assets tend to be very fragile. They don't have very robust TCP/IP stacks. And so you push them too hard, you scan them too hard, they might fall over. So that's kind of an interesting learning thing, which we purposely do every now and then. Different security assessments and these different things. In terms of lecture classes, just grab them early. As soon as we start talking about intro to programming, on the engineering side, almost every intro to programming class devolves into some sort of mathematics class. Here's how you would work with this, curve fitting, regression, these different things like that. And so oftentimes we'll have them go out and find a data set, pull it in, and work with it. So from right there in the get-go, how do we start to think about ways of handling credentials, like securing credentials and all these different things. A lot of these things are in Jupyter notebooks. And so my students would love to share them up and start to post these things to GitHub, which is phenomenal. And so talking about stuff like, okay, what if you goof and you put credentials then up on GitHub? Here's an example of someone that tried that. They leaked. It was an intentional thing. They built a honeypot where in their honeypot, they built a honeypot, and then they built a GitHub repository where they made a commit that included an SSH username and password key. And I included the username and password right there in the middle of the screen. And so it's not an obvious user, deploy button. And the password, most people would look at that password and say, well, that's pretty good randomized password right there. And so he then ran this experiment. How long does it take before someone is able to get into via SSH into the honeypot? He sees the first people brute force attacking it within 68 seconds, which actually matches with my colleagues that teach using Raspberry Pis. If it's not on an unsecured network and you've installed a Raspberry Pi with default credentials, they estimate it's minutes then before someone's into that device. But the first time that someone used those lead credentials, so they found it on GitHub, and then they find the device and then start to use those credentials. It took about a half an hour between the commit on GitHub and that. So working these concepts into the earliest programming classes and making these modules along the way that build up, I think is absolutely crucial. So real quick, I'll finish with some conclusions. It looks like we got some questions over here. I'm excited to answer. So we see an explosion of cybersecurity incidents related to critical infrastructure. And I think those highlights a dire need to invest in relationships, expose engineers to cybersecurity concepts, but also vice versa. Expand availability of critical infrastructure facilities and training to people outside of the traditional engineering fields. Come run a distillation column. I'd love to have you there. Or I'd love to just come and talk to your class. It could be virtual or something like that. And along the way, we need to start creating more modular, multidisciplinary content that educates on critical infrastructure and how we can protect it. So with that, I'll thank our sponsors of our laboratory space here. And I'm happy to answer any questions. I'll give you my email address and a link to the website. Okay, so far we've got a couple questions or a handful of questions. Let's say, to play devil's advocate, what percentage of the workforce work in critical infrastructure? Yeah, that's the thing. I think it'd be great if we provided a baseline education that in case you went to work for one of these things, that you would know some basic concepts and you would know where to continue your education on. So you'd probably go either back for master's or PhD with somebody, or more likely you'd go to work, you'd go and start working on certificates in certain areas and so forth. But we do, I think, need a baseline education, or we do need some baseline education and knowledge base for a lot more of our students, because it's clearly a problem that we're having with critical infrastructure. So should we be integrating this material into a general engineering curriculum? Yeah, absolutely. Yeah. Earlier in the presentation, we mentioned that we weren't budgeting enough for critical infrastructure upgrades. Absolutely, yeah. When I do, I've given a talk before where we walk through how you would design a piece of equipment as an engineer, and if it costs $1 million, I'll say I need 20% on top of that. We just use a figure, 20% typically, and that's going to be how much the control system is going to cost me. And then we'll add another 20% fudge factor on top of that, that says these are other things, various things, like it might be the network connections that allow for connection through a DMZ to like a corporate network or something like that. But there's also a ton of other things. It's 20% miscellaneous costs. So we're not really budgeting for how we can do upgrades. My students, if they design a reactor, they'll tell me after 4 years, I need to take apart this reactor, take out the most we're going to have a little bit extra downtime because we need to fix these things like that, but none of that for control system upgrades or anything like that. So it says, should the infrastructure simply not be built because it isn't profitable if we perform all the upgrades? No, obviously we need to build it, but we should probably rethink the budgeting process and say we need to actually contribute and carve out more resources from the beginning to make sure that we have the ability to safely run this equipment for years and years. We do that on the process safety side. We make sure that we have the resources needed to run it safely. We should think about the budgetary resources to make sure that it stays, from a cybersecurity point of view, safe as well. All right, so hopefully answered the chat questions so far.
David, the talk in the chat was duplicated in the Q&A session, so I think we're up to date on that. But awesome. We do have a few more minutes if anybody wanted to pose any additional question or comment.
So I'd be happy to talk with anybody about critical infrastructure, give you tours of the laboratory, or maybe even virtual or something like that. Give you some experience potentially with some control systems and what it's like, what's different about it. If you've never experienced how you program, say, a PLC or something like that, it's pretty wild. The original logic controllers were all wired based. It's wires and relays. And that's mimicked now in the programming languages that used for PLCs. And so it's not like anything you've ever seen before. I know I did several AI courses and got exposed to some really wild languages I never thought of before, Lisp and these different things. But PLC programming is a totally different beast, with trying to pretend that you've got this logic flowing down relays and wires, even though you're writing it as code. It's really wild. It's cool. But if you ever want to see anything like that. So can I talk a little bit about the role of simulation in testing these systems? That's great. Yeah, we actually set up 3 different systems. We set up a test system, a development system, and a production system in our laboratory. And so we do a lot of simulation on the test and development systems. And so it's not just random signals or pre-programmed signals, but we have signals that deviate and say that we have some sort of process event that's going awry. And so then we look at different control schemes on that, especially on the safety instrumented system side of it. Yeah.
I would love to add, while you're reading the question, David, that at CERIAS, we were lucky enough to receive a $10 million donation from the Department of Energy that set up the SOLAS laboratory, which is emulatics, so emulation and analytics for cyber physical systems. So that would be an area that we would love to be able to collaborate with anybody in the attendees list, as well as with Professor Henthorn and his lab at Rose-Hulman.
That sounds awesome. And another question about how does your funding look like? We are primarily an undergraduate institutions. We have a few master's students. It's mainly undergraduates. And so we work very closely with companies. And so you see that list of people who support the lab. They tend to be large companies that support the laboratory. And so we mainly seek corporate funding for these things. Yeah. But yeah, as mentioned before, the funding, then there's certainly funding from a number of governmental agencies as well. We're very much on the corporate side. SonicWall just announced 0-day flaws in their products. Any comment? I've never used any SonicWall product. Yeah. Yeah, I wouldn't be able to comment on that. Thanks.
Well, as we roll up at the bottom of the hour, I again will take this opportunity to say thank you both to our attendees for attending the talk today, but specifically to our invited speaker. David, it was great to have you.
Thanks.
I hope this, as I mentioned before the talk, that this is just the start of a relationship between our labs and your lab and collaboration. To close out, I wanted to mention a couple of comments. One that we will have these weekly seminars on Wednesday afternoon at 1:30 p.m. Eastern, continuing through the end of this month. Then we will go on to hiatus for a few weeks and pick these up at the start of the fall semester at Purdue, which our classes start August 23rd. So that would be like the 25th. You can get this off the internet, but the 25th of August, we'll pick that up in the fall. They will move back to our normal non-summer time as 4:30 in the afternoon. That's because this is actually a 4-credit class at Purdue for our students. Also, on that same note, we do have a few openings that are open that are on our fall slate. So if you can make a recommendation of somebody who has a great talk that's out there. Again, we make sure that we do not slate any product talks, any sales or marketing talks, or any product demo, that they are informative talks that fall within the area of cyber and cyber physical systems, with the focus on security, privacy, resiliency, autonomy, trusted electronics, and explainable AI. So if you'd like to recommend somebody, I have dropped an email into the chat box. Please feel free to drop us a name, whether it's yourself or a talk that you've seen elsewhere, or a great researcher or program manager that you would like to recommend. And then finally, I wanted to include that while the agenda is not up, we are hot in planning for the 22nd annual CERIAS Cybersecurity Symposium at Purdue University. The dates this fall will be October 19 and 20. Mark your calendar now and watch our website for when registration opens in, I believe, August. The registration will open. But I have obviously have some insight in who are invited speakers, and we're already very, very excited about the 22nd iteration of this. So with that, again, thank you to everybody who's on this call today, and we look forward to seeing you all again next week. So take care. Bye-bye.